Uh, Thank you for the kind invite. Hi. So I can be here, right? Hi everyone. Cannot make it on site. I'm actually on the airport to the ICRA. So my talk today is focusing on generalized autonomous driving at scale. So basically, I'm gonna cover two works. Basically, the first is a word engine where we try our effort on the post training for the physical AI, and the second work is gonna be appeared at CPR this year. It's about the scalable into real code training, and we're going to talk about some insights, some experiments on the way to scale up simulation for massive production for autonomous driving. So first thing first, there is autonomous driving has entered into the second half, right? So the easy miles are done. The industry knows it, and Tesla is pushing the free-scale data and warehouse scale compute. So this is the report that I exert from their recent report. And also we can see Li Auto. This is a very popular automotive car manufacturing in China, is betting on the end-to-end learning with VLA and Horizon. This is a algorithm provider in China is training edge cases through large-scale scenario integration. So every major player is searching for the same thing. That is a way to crack the last 12% of the driving issues. So here, the figure on the left shows the probability versus the probability of the driving cases, where on the x-axis, we divide into 3 cases, where you have the normal driving cases that will happen a lot. And also we have this purple gray area that is the safety critical near miss events. This is the area that we want to focusing on. And also we have the accidents area where the probability is very, very low, but if you consider the cost, it will be very like resource intensive if this kind of thing really happens. So the voice issue boils down to how are we gonna grab the last 30% problems or challenges in the post end-to-end open planning era. So this is a key. I believe most industry collaborators are focusing on. So today I'm going to introduce the first work, which is the word engine. It is toward the era of the post training for physical AI. So this is a joint work by Ting, by Li, by Hoping, and by Houghton. Houghton has just graduated from the NTU to join Xiaomi, another collaborator we are working on recently. So the idea is very straightforward. We can see this is a comparison between the LLMs is portraying on the web scale text, and also this is portraying with our variable rewards. We can see the pipeline from the policy, from the output, and we have a verifier. And the reward, we have some scalar reward update as a constantly. And also on the right hand, we see physical AI needs post training. Why is that? We already pre-trained on the scale real data, and the question is how to effectively utilize the post trade, right? So here, which is different from the what they do as a common practice in the LMs. For the physical AI, you have a physics, so collision, safe distance, and the constraint certified or not. So based on that, we have a reward design mechanism. So you cannot process a like near miss, right? But you don't need it to. So driving has its own verifier physics. So for example, a collision is a collision. It has actually either holds a safe distance or it doesn't. So the reward is not a matter of human judgment. It is computed automatically from the laws or from the physical common sense, like the driver do, right? So this is a key part. So what is missing is the data to apply it to it, and the right data is not collected. So it is constructed from the failure, the real world is too rare to provide. Okay, so this is a diagram. And this slide, I think this part is quite important to understand the whole philosophy. So actually, word engine is not archived yet, but we already open source on the GitHub. So it's a very long project that consists of 2 years. So it's a group of research papers or projects, whatever you name it. So it starts from the motivation that I mentioned. So we are trying to solve the 20% of the corner cases, like in the purple or red area. So basically, in the before, we have this passive data collection where we have this rare safety critical events, like the purple triangle sets indicate here. So this is a rare case. And for most novel driving distribution, we have this advanced distribution. So this is operational boundary, something like this boundary shows in the top left. So there's a paradigm shift that we want to offer. Basically, that is to sue the word engine, the data engine, to generate synthetic variants so that we could alter the distribution of the original passage. Say, for example, I often use these 80% versus 20%. So, for example, we can alter and augment many OOD states or also distribution scenarios. Say, for example, 50 to 50, and have this safety critical driving distribution so that the model, in this case, the word model can focus on the solving the cases. So in a nutshell, the the bottom part of this slide shows the pipeline where we do this word engine philosophy into the massive production. So basically, the first step is the training. So you have many real world logs. So this what we call the base physical AI agent. And then you have this long tail event discovery where you identify the their events and accumulate like what they do in the dagger. So enable the base physical AI agent to you have this is a keeper where you have the post training with word modeling. So basically, you have the word model interacting with the environment, generating many safety critical cases in terms of the trajectories, and then use RL. So RL as a feedback, yes. For example, you have this collision as a reward to give feedback to the system. And then this deals with simulation and deployment, where you have the simulation validation on Kala or other simulators, and also you have this real world deployment for the method production state. I will show some results that is in collaboration with Huawei to have this MPI metric improved. So this is a general idea. So let's dig down into some details. The first one is the data engine part, where you have this data engine to generate photorealistic reconstruction. So what does it mean? So this is a work that in collaboration with the other partner reviewer, we have this this pipeline built on the 3D Gaussian spec. So each thing is composed into a single graph. Every element is reconstructed from the real world logs as a set of Gaussian 3D Gaussians. So this gives us two capabilities. So the first is the full thing editability, which means we can reposition or reroute any agent independently while the surroundings stay very real. In terminology, is photorealistic. And second, this is a three viewpoint rendering. So the scene renders from any camera pose, not just what was recorded. So by multi-traversing. So this is where exactly the title suggests. So this is what makes a closed loop simulation possible. So the core algorithm is what we call the MTCS, multi-traversal Gaussian strategy. So this is across more than if I remember, more than 12,000 reconstructed real-world assets, enabling thousands of rollouts per scenario at the scale that RL possibility demands. So this is work. I think one of the most important work within this Word Engine group project. Another project I want to mention is the behavioral model, which is a combination. So this work deals with the trajectories is not a raw perception input, of course. Given the current scene context, like for example, map topology, historical agent states, and the ego vehicles action. So it generates a future generates therapies for all surrounding agents simultaneously, maintaining multi-agent consistent throughout. So the motivation is 3D-GS, like I mentioned earlier, gives a real work, right? But a static scene is not enough for the closed loop training, right? So what it matters is how surrounding agents behave and whether the behavior can challenge the ego agent in meaningful, in feasible way, right? So this is where this work starts in. So the scenarios on the right side is rendered directly from our 3DGF reconstruction pipeline, providing augmented rollouts for reinforcement post-trade. Yes. And this third work, this is also a follow-up work that we just submitted recently. So with thousands of photorealist rollouts now available from the real world scenarios. So the question becomes, how do we learn from that? Right? So standard imitation learning learns what humans do, RL means what the agent must not do by enforcing the negative reward. So we formulate post-training as behavior regularized reinforcement learning RL. So the agent optimized for safety, comfort, and progress. Here we see on the right, so this is the KL constraint. So basically the red indicates pre-trained policy. This is actual prior. And the right one, this is a post-training policy. This is updated. So by enforcing a KL divergence penalty, it keeps the post-train policy close to the pre-train part. So otherwise, it may not overfit to the rare scenarios and forget how to handle every day driving. So this is work I really like. So this works together. One anchors the distribution, the other example. This is the result is a policy that is not just a pre-trained on what the word looks like, but post-trained on what the word demands. Okay, so this is a key idea for the especially the data engine part. Let's see some results on the work. So these are the results. You can see. I'm not sure on side the screen is clear enough. So for the engine, this is the distributed dots in dark blue. Because of the number of samples are very rare, so I cannot draw a line, a curve. And this shallow blue, these round circles, these are the imitation learning results. So we can see the x-axis is the training data sets. So if we extend the training data sets, the PDM score, the higher the better, right? So common cases, this is the open loop testing for the common cases. Skill, predictably, more data helps. This is easy common sense, right? And when we do the rare cases, it saturates. So which means if we simply utilize the imitation learning without the feedback of the data entry for with post-train RL, so it starts. So we have this is where the work engine starts in. So as we extend the training size, the PM still keeps going or improving. So the curve flattens, more data starts helping. So this is where more data climbs the curve for the engine break safe. So as you can see, you can also see the right figure on this slide. This is closed loop testing on the rare cases. So you can also see on the rare cases, it improves more for the word engine pipeline. So I really think this is a very good pipeline. And the conclusion is post-training from the 50K things gains. This is gains equivalent to like 14 times more data, the efficiency versus the performance gain. Okay, so I think this is the most important results I want to deliver in this talk. For the other ablations, effectiveness, and also the other stuff, I'll probably skip due to the time limit. So here, this is an ablation. You can see here. So this is an ablation where you can see the post training with the word engine. You can focus on the rightmost metric, which is the causal PDM score. So you can see base model starts from the 60. If you add post training on common logs, on rare logs, and on rare synthetic replace, so the performance will improve way more. And finally, we have the post training with word engine. So it bumps up from the 60 to the okay, and as for this slide, I also like the result here. So scaling up our lab level on the new plan to the Huawei real world data, tested in Shanghai, millions of miles. So production level scale validation. So it shows that the, for example, so this is production scale closed simulation. It accounts for like 80,000 hours of real world driving log as the end-to-end base model. And after the word engine post train, so the cutting collision rate dropped like almost 50%. So basically 55.5%. So what I'm talking here is this one. So cutting collision. So the N stands for the number of trials we have tried already. So it's an average of the all the draft files. So we can see this is super efficient, and this is the first time I think word engine applied to a production system, not a research, merely research backlog. So these numbers have real consequences on the real roads. So I'm really excited about that. And for the production scale closed simulation, we can see a comparison of the 4 cases. So here, this is the base model where we don't rely on the post training with data entry. And you can see all of the base model, they will collide as the video goes to the end. So you can see here, you can see my pointer, right? So this is a base model where it collides with the cutting black vehicle, but where in this case the work model engine it stops and then it goes up on the road. So this is another video. I don't think you can probably you cannot see the sound here because yeah, I just saw the key clears setups I didn't make. So probably you won't hear the sound. So basically, this is on-road testing. It runs like 200 kilometers without a single disentanglement. And I will go like here. Those are the elevator road on in Shanghai. So here the individual most power in turning to the canyon after detecting the word engine models interferes. And this is nighttime testing. Yes, with the rainy road. And this is obstacle that you have to take care of that. This is thrown on the road. So you can safely bypass and proceed very smoothly. Here the Eagle vehicle is an e-bike slightly introduced into the thing. I safely bypass and proceed very smooth. All right. So this is a right turn. So the car needs to pay attention to the pedestrian and stop. this one, this is also a very typical scenario where you have to wait for the traffic light. Enters the intersection, the first oncoming vehicle appears, the vehicle slows down to ensure the safety without interfering. The second ongoing car, and yeah, just in time the traffic was about to turn red, and it quickly goes through this area. So this is a really impressive and many thanks to the Huawei engineering. So I mean, we have like 5 or 4 students working as interns and full-time in Huawei, but they provide like more than 20 engineers incorporating the system into their system, into the Huawei in-house system. Really excited to that. So this is the last part of this word engine project. This is the takeaways. So why this matters beyond auto driving. So it's generalized to physical AI in the open world. So it not only implies for the robotics, but also it applies in the humanoid robots. So we see the case is word engine is a framework. So yeah, everything is good. Okay. So the domain is auto driving, but it can extend to the problem itself is universal, right? We can apply to the humanoid robots to the drones. Okay, so we also open source the project. So it's a production validating. So the missing infrastructure for this is what we deem as the missing infrastructure for the physical AI process training AT. So the patent here, the GitHub is here. We come to check it out for that. And the second word, so the link between these two words, word engine is a algorithm and data engine that consists of 2 parts, data and generation with where all the distributed with the algorithm on being focusing on the word modeling with agents with feedback. So this work, same skill, which appears in the next week or in a few days at CPR. This is learns to driving while the real world. I mean, so it basically fill out the data by simulation. So how are we going to do that? This is what I've heard by my PhD, Hao Chen and Qian Yu, and another Fortune by different last name, and Jiazhi and Hao. So here, this is a little bit background. Recent foundation models have shown that scaling from the internet can consistently improve capability, right? From language model ChatGPT to image generator, Nano Banana, for example, right? So this slide I just showed earlier, just a quick recap. So the normal data is less valuable, and but it's a scalable, right? It's the action, expert action, right? Critical data. So this 50 critical driving events is valuable, but it's non-scalable, and it doesn't have any expert data. So the real world data scaling is bottlenecks. Okay, and so introducing the real world simulator. So basically, we all know the definition of word model, right? We have this worldwide data. So word model basically defines the current state given the prompt. So here in this example, this is what happened if I go straight. This is a prompt, and to output the next frame, which is SP plus 1, and ideally, it will present several good properties, which is the real-world dynamics, minimal visual gap, and we try to optimize to improve the scenario generalization and improve the decision-making process. So video word model with neural rendering and with the hybrid simulator, basically from the real and simulation. So simulation, we can safely and cheaply scale the critical the critical data and try any times to get a safety behavior. We never need to worry about interaction risk, and because we are in the simulation work. So how to generate and utilize and scale critical data for end-to-end driving. This is a key that we want to emphasize in this work. So, so the first is generate. We have a scalable simulation pipeline that simulates diverse and high fidelity reactive driving scenarios with pseudo expert demonstration. And we want to utilize an effective sim-to-real co-training strategy that improves robustness and generalization simultaneously across various end-to-end partners. And also for the scale, can comprehensive recipe that reveals crucial insights into the underlying scaling properties of the real learning system for this end-to-end autonomy. So here, this is a little bit recap of the past work. So we have this 3DGS neural renting. We have this work. So in simulation, we can safely and cheaply scale critical data mentioned in the MTGS that I talked earlier, and try many times to get a safe behavior. You never need to worry about interaction risk because we are in a simulation work. But for this real world, how are we gonna utilize this simulation pipeline? I think this is one of the important takeaways of the talk. So we have this so-called off policy perturb planning. So basically, to get into the OT state and get out of it. How are we gonna achieve that? So the first stage, perturbation, example, diverse, possible perturbations to the ego trajectories, maximizing coverage of the space. So perturbation allows ego agent to explore safety critical situations as many as possible. And for the second stage, planning, we have this with this OOD states, we further need corresponding proper action supervision to form complete training data for end-to-end policy training. And here we use two different kinds of pseudo experts to generate these trajectories. So the first is recovery-based expert retrieves trajectories. So it steers, basically steers the policy within the human trajectories manifold. So towards human-like yet cautious behavior. And the second, privilege. So this is the privileged planner-based expert generates the trajectory that maximizes optimally towards primary strategy. So this comparison helps us better understand what kind of pseudo expert is more suitable for driving policy. Okay, so here we start from the example. Once real scenarios through the perturbation, we generate three different simulated interactions, like simulation 1, 2, 3, with the white vehicle. Okay, and each is paired with a proper solution shown in the red point. Okay, next we zoom in on the third one. So for this third one, the ego vehicle first moves towards the white vehicle and successfully recover from a situation. Here we show 4 examples of simulated OD scenarios, okay, including one center lane drift, near collision, and leaving road and cutting. So after generating simulation data, the next question is how to use it effectively. We employ a simple and yet effective sim-to-real co-training strategy. So basically, it can maintain human driving distribution and reduce visual degradation. So we apply sim-to-real to multiple end-to-end policies, including a regression-based LTF, diffusion-based diffusion test and score-based TRS. So the simulated trajectory from pseudo experts are used together with real-world data for individual. Okay, and we further study whether expert supervision is necessary. So we only obtain rewards for simulated data without manipulating, which is like offline area. And this is a little bit detailed I will give for that. So we choose to widely use the real world driving that are doing examining not hard and not fast. So for example, on that part, which focuses on the robustness and the safety, the critical scenarios didn't scale achieve a strong result. And on that test, which evaluates generalizations and scale also consistently improves the performance. So these results show that co-training in physical can improve both robustness and generalization for any end-to-end policy. And to analyze the scaling property of simulation data, we do simulation for multiple runs of prediction to increase the data set.
So Hongyang, sorry about that, but we are running out of time, and I would give you half a minute less because people also want to ask some questions, and then we need to jump to the next speaker. I'm very sorry about that, but
okay, sure.
your half hour is over. Okay.
Okay,
good.
Sure.
Yeah, go for the takeaways. Thank you.
Okay, so the takeaway is so by introducing this tool, I think scalable simulation with super expert unlock the inherent potential of available real world driving data, and also we see some real co-training improve both in robustness and generalization. And also we see exploratory expert and interaction environment increase the effectiveness of the simulation data, and paired with multi-model modeling capabilities exhibit more data scaling algorithms. So we open source it, please try it out. So that's awesome.